Taking a look at our list of things to do, we've got some stuff to do today. We're going to do a ranking test real quick first, then we're going to go over homework. And we're going to do some new content that's just going to kind of solidify and, help us get all this. And we got some more problems to work on for tomorrow. So just to get our heads in this physics game here real quick, I've got a cute little ranking test. This one's got cute little, oops, you can't see it though because it's frozen. Sorry. Oh, they're so cute, these little cars. They're driving. In each figure below you've got cars' velocity shown before and after some time interval. It's the same time interval, but that doesn't really matter in this case. Okay? My question is, and the task that I want you to do is to rank the magnitude of the change in velocity during the time interval. Okay, so your eyes are up here. You're working on this. Rank the magnitude of the change in velocity during the time interval. I'll give you a minute to think by yourself, and then I'll let you talk to each other as well, of course. Rank the magnitude of the change in velocity during the time interval. Go ahead and talk to your table mates if you'd like. Have a conversation. See how we're doing. You got an answer? Have you talked to each other? You got an answer? You're ready to go? Okay. Patients, are you guys ready? Do you have an answer? But you have something that you feel confident-ish about? Cool. How are we feeling over here, ladies? Feeling good? All right. I didn't get whiteboards out today because I don't know that we're going to need them for more than this one. I can't remember for sure. Somebody want to give us an answer? Throw it out there, Gosha. How about you got?
A greater than C greater than B equals D.
A greater than, you said C, is that right?
Yeah.
Greater than B is the same as D? We agree? Have a little difference? Go, Stella.
You said C greater than A equals B equals D.
Whoa, okay, that was a lot. Say it again. C.
C greater than A equals B equals D.
You guys have this one too? Somebody want to defend? Or did you guys have an answer that you wanted to throw? This one, okay. So let's look at B and D first. Ben, did you guys agree with one of those, or do you have something different back there?
I agree with C is greater than B.
Okay. So all of them have this B and D are the same. So let's look at B and D first. What's the change in velocity for B? 10? 10 meters per second? Yep. How about D? 10. So this one is slowing down. This one is slowing down, but we're just talking about magnitude, so we're good there. How about A? Also 10. Now, if we were going to do non-magnitudes, if we were just going to do the change in velocity literally, come on thing, then this would be positive 10, And these would be negative 10, right? Is that right? Change in V. Negative 10 meters per second. Let me be a really good kid. And then there's C. What's C? What's the change in velocity for C? Negative 20. Why is it negative 20?
Because it goes from 10 to 0, which is 0 to negative, which is awesome.
Yeah. So we got the change in velocity is really going to be final minus initial is negative 10 minus 10 is negative 20 meters per second. So it looks like if you were going to do it without the magnitude, it would be A is greater than B and D is greater than C. Does that make sense? A lot of people want to make this one what? If you're going from 10 and negative 10, if you just subtract those, what do you get? 0, right? That's the little tricky part here is really paying attention to that. Yeah. But I think that the magnitude, A, B, and D are the same. That looks right to me because they're all 10. And this one's bigger, even though it's going backwards. It's a negative change. Its magnitude is 20. We good? All right. Next thing on my list of things to do was homework. Does that make sense to you guys? Okay, cool. I thought I just wanted to make sure that I didn't ignore questions that existed. Homework questions. So I asked you for today to do page 57, 1 and 3A, 21A and 16 from page 75. Questions on those that you'd like to go over? They go okay? Do you want to know answers at least? Maybe that would be helpful. Let's take a look. So on page 57, so listen carefully because I'm going to just read them to you here. I guess I can write them down as well. Page 57, number 1, the answer is, what did you guys say? Anybody get anything? First one. Page 57, number 1. 0.85 seconds. That is the right answer. Number 3A is 5 meters per second. Stinker. And then on page 75, that rain is really loud. Holy cow. 21A. I don't know why I wrote those in out of order. I apologize for that. That's kind of weird, right? I apologize. 21A, what did we get? Negative 15 meters per second. And number 16, 4 seconds. Questions on those? Are there any of them that you want to go over? I'm very, very happy to discuss them with you if there's anything that you want to go over. Yeah. 16? Absolutely. Yep. Let me pull a different page up here. Question 16. Let's do it. It says, a car traveling in a straight line has a velocity of 5 meters per second. After an acceleration of 0.75 meters per second squared, the car's velocity is 8 meters per second. In what time interval did that occur? So what are we going to start by doing, guys?
Our givens.
Boom. Yeah. Our givens. So what's one thing we know? Our velocity final is 8. Our velocity initial is 5. Even without looking, should our acceleration be positive or negative? What do you think? Positive. Yeah, it's positive because it's speeding up. Yeah, and it said that it's 0.75 meters per second squared. We kind of talked about this yesterday. How are we feeling about these units? Do you want me to write it out for you, or are we kind of okay-ish? Acceleration is velocity, change in velocity per time. So that's meter per second, or meter per second squared. In what time interval did this occur? So we've got our givens, we've got our unknown. Now we need an equation. Anybody want to suggest an equation for me?
The displacement over time.
Say again.
The displacement over time.
Displacement over time
The
is velocity, right?
Delta V.
Yeah.
You want delta V over T.
Delta V over T. Yeah. And you can totally write it that way. I get lazy, and because I don't want to write this out because I don't have a delta V written out here, I'm just going to do VF minus VI. Yep. So, and either one is okay with me. This is the one I usually start with. Because it's got all the things in it, right? So this is, and the process is going to happen today. You're going to look over here, VF, VI, or VI, VF, A, and T, VI, VF, A, and T. This equation has everything that we know and the thing we don't know. This is the game that we're going to play today. Now we just need to solve it for T. I want to get T all by itself and in the numerator. What do I do first? Multiply by T. So let's do that. Multiply by T on both sides. And then I need to divide by A on both sides. So I've got T is equal to VF minus VI over A. Then I can plug it in. I've got 8 meters per second minus 5 meters per second divided by 0.75 meters per second squared. I can plug in my numbers to my calculator, right? And that's all well and good. And I get, I don't know, what did I get? 4? I would like you to get in the habit, though, of looking at the units and analyzing the units to make sure you didn't make a silly algebra mistake. Because believe it or not, even with my smartest students, algebra mistakes happen all the time. So I want you right now, regardless of whether you got the question right or wrong on your homework, I want you to look up here. Okay, eyes are up here so we can look at these units. We're going to do some dimensional analysis. My chemistry friends and I both love this. This is one of the times when my chemistry friends and I this is all about for everybody. Okay, I've got meters per second minus meters per second. What is that going to result in? Do they cancel out? It's just going to be 1 meter, right? If I have 7 apples and you take away 3 apples, what am I left with? 4 apples, right? The units stay the same when you subtract. So I've got meters per second minus meters per second. So that's going to be meters per second on the top. And then I'm dividing that by meters per second squared. Now, if you learned one thing in 3rd grade math, when you were learning how to divide fractions, it was that dividing fractions is the same as multiplying by the, that was not very loud. We're going to try that again because it's so important and I want to make sure you know it, right? If we're dividing by a fraction, it's the same thing as multiplying by the
reciprocal.
Yeah! Reciprocal means you flip it. So we're going to do this. It's the same thing as saying meters per second times seconds squared per meter. Okay? I've got meters on the top, meters on the bottom. What happens to those meters? Say, see you later. We don't need you. I mean, yeah, we don't need you. And I've got seconds squared. That's seconds times seconds. And I've got 1 second on the bottom. So it's left with, so I got seconds squared on the top, seconds on the bottom. What does that do?
Second squared minus second.
Yeah, so you got 2 minus 1 is just going to leave you with 1. That's going to cancel with that. That's left with seconds, which shouldn't be a surprise since we were looking for a time. Okay. But by writing the units in here, hint, hint, when you take a quiz over this, you need to make sure you write the units in here. Okay. Well, by writing the units in here, you can double check to make sure that your units are correct, which means that you did the algebra right, which is a nice check for you while you're doing it. How are we doing? Okay. Were there any other of the homework questions that you would like to go over before we move on to other stuff? Okay, cool. All right. I would like to, what am I going to do next here? I got to double check my list here. We're going to do some sign stuff. Here we go. So on your notes, somewhere on your notes, yesterday I told you to get out a brand new piece of paper and you're going to write a bunch of stuff on that brand new piece of paper. Yeah. So now I don't want you to write on that piece of paper. That's why I was telling you that. Write on the back of it or write on the next piece. Because where we started yesterday, this one here, I need you to leave some space below because we're going to come back to that in just a minute. But before we do that, I want to have one other conversation with you that we didn't have yesterday. Well, we kind of did. We just didn't formalize it yesterday. Okay? And it has to do with the signs of velocity and acceleration. That rain is just intense. Holy cow. All right. So on your paper, we're going to make a chart. At the top of the chart, oops, I'm going to make my lines just a little bit less. There we go. At the top of the chart, I want you to write velocity in one column, acceleration in the next column, and motion in the third column. And the game here is to figure out what different kinds of motion mean. So we're going to start with a hopefully really easy one. If you have a 0 velocity and a 0 acceleration, that's pretty unexciting, right? Tell me what's happening to the object if you have a 0 velocity and a 0 acceleration. It's not going anywhere, right? It's not moving. It's not speeding up or slowing down. There's no motion. So let's make it a little more exciting. If I have a positive or negative velocity and 0 acceleration, tell me about the motion of the object. Is it, go ahead, what did you say? Constant. It's moving at a constant speed or constant velocity, right? I'm going to have a skip a line and then draw a line underneath. Okay. And then on the next line, I'm going to ask you this one. If I have a positive velocity and a positive acceleration, what does that mean? What's going to happen to my object if I have a positive velocity, positive acceleration? Is it speeding up, slowing down, or staying constant? Speeding up, right? This is you're driving 30 miles an hour in your car and you put your foot on the gas, you're going to speed up, absolutely. We graphed that yesterday. We'll skip a line. How about this one? What if I have a positive velocity and a negative acceleration? So you can think about the positive acceleration. That was like putting your foot on the gas, right? Okay. Negative is like putting your foot on the brake. You're going in a positive direction, but the acceleration is negative going that way. What's going to happen to your motion? You're going to slow down. That's right. Here's my next question for you. This is where it gets a little bit funny. What if I have a negative velocity. First of all, what does that mean? Describe to me what a negative velocity means. Where are we going?
Backwards.
Backwards. I have a negative velocity, but a positive acceleration. So the secret with positive acceleration means that it's pulling this way. So I'm moving this way, but the pull is going this way. What's it going to do? Eventually it'll stop, but on the way to stopping, it's going to slow down, right? You're just like, I have to stop, like, boom. Yeah, if it's a really big acceleration, sure. Yeah, but it will slow down. This one's one of those funny ones that you just have to kind of process a little bit. Let's add a couple more. What happens if I have a negative velocity and a negative acceleration? So again, this is like the direction it's pulling on you in, right? So if I'm moving in the negative direction and I've got a negative acceleration, what's actually going to happen to my object? It's going to speed up, slow down, or stay constant? Is that right? If they're the same, then it's going to speed up. That's exactly right. Yep. So, and we're just talking about speed, right? So it's not the velocity because the velocity is here. That's why it's really important that we have that distinction. So speed is literally just what's on your speedometer, right? Not the direction that you're going. That's the trick. If the velocity is, excuse me, 0, and the acceleration is positive or negative, doesn't matter, what's going to happen to your motion? If your velocity starts at 0, and then you have something pulling on you either this way or this way, what's going to happen to your speed? Ben's doing a dance back there. He's like, why is it going to go up? Can it go down? Can the speed get any smaller than 0? Speed can't go down below 0. That's the floor, right? Can't go down below 0. And if you have something pulling on you, you're not going to stay at 0. So by process of elimination, it's got to be speeding up. These 3 are the funny ones. So you may want to put little stars next to them. These are the ones that are not as intuitive, if that makes sense. Okay. I want you to use this chart. I'm going to give you some problems to look at here, some conceptual questions. There are 3 of them. I'm going to give you, let's see, so I can fit all of them on the page. No, I lied. I'm going to do one. What am I going to do? Can I fit that 3rd one? There's a 3rd one, isn't there? Hello. Sorry. Should have had this organized better. Isn't there a 3rd one in there? Oh, it's way down there. Okay. We'll just do these 2 first. Take a look at these questions. I want you to read them by yourself. I want you to think about them by yourself for right now. Okay. And then we will discuss them. I really appreciate it. Thanks. Take a look at those 2 questions. I can retrieve that last question for you. There it is. And there's that 3rd question. Take a look at all 3 of those. Maybe jot down some answers so that you don't forget, because it's kind of hard to keep 3 answers in your head at the same time. Okay. Grab those 3 answers, put them in your brain, and then we'll let you discuss. All right, why don't you have a conversation? Let's focus on that first question, just the first one right now. Have a conversation at your table real quick. How are we doing?
So,
Answer?
no,
Oh, question.
is the rock at maximum velocity already, or is it just being dropped?
Good question. Good question. Looking for the pieces there, right? Let's talk about it. Let's talk as a group here. So the question says, which of these motions is not at a constant acceleration? Not at a constant acceleration. A rock falling from a cliff, an elevator moving from the 2nd floor to the 5th floor, making stops along the way, a dish resting on the table. So first inclination, what do you think? Which things are not at a constant acceleration? What's that? Elevator, right? Every time you ride on an elevator, you know those little, like the funny feeling you get in the pit of your stomach? Do you know what that's from? What's that? The acceleration, yeah. Accelerations often cause your body to be like, whoa, because it's not what you're used to, right? So yeah, absolutely, the elevator is not moving at a constant acceleration. How about the dish resting on the table? What'd you say? Constant acceleration of what?
0.
Of 0? Sure. And then what about the rock? What are we thinking about the rock falling from the cliff? First inclination is that constant or no?
If it was just started, it's falling. But if you measure it falling off the cliff, like rolling off the side of the cliff, it started falling.
Yeah, so I think they mean like 1, 2, 3 now, right? So while that frog falls, is he at a constant acceleration? We haven't really talked about it yet. But the answer is yeah, he is. He's being accelerated downward. But you were fussy about what?
What's the rock at maximum velocity?
Okay, and it reached its maximum velocity or its terminal velocity. So if it's at its terminal velocity, then is it accelerating? It isn't. So if it's not accelerating, the acceleration would be 0, right? So when you ask that, you're introducing another variable, and that variable is air pushing up on it. Okay, so the real answer is that if you take air resistance into account as it's falling, then the acceleration isn't actually perfectly constant. Okay, as a physicist, I'm going to say yes, it is, but as an aerospace engineer, someone would say no, it's not. There's drag, right? There's this air stuff. So we're going to ignore it most of the time. But if we include that air resistance while it's accelerating, then it's going to be changing. Yeah, good question though. Good point. All right, talk about numbers 2 and 3 real quick. Go. See if you can come up with examples for each if the answer is yes, I suppose. If the answer is no, then tell me why. It's not talking very loudly. Are you having like brain conversations? You're thinking still? That's okay. You're allowed to think. So can an object have a 0 velocity with a non-zero acceleration? Yes, sure. It was on that chart that you showed us, so Why would you not? Yeah, I mean, sure, go.
Well, for example, I was thinking about if you've ever been tubing, you're just kind of like chilling in the water until
Okay.
someone accelerates the boat, and then there's like a big jolt of
Okay.
acceleration, and then you get good velocity. The acceleration is good for the big velocity.
Oh, so it's kind of an instantaneous, non-instantaneous kind of thing? Yeah. So that is kind of there, where you're sitting there and then you're getting pulled. But I think the timing is a little bit funny on that, and I think there's some friction and things like that. But I think that's a good start. Yeah. Any other times you can think of when you have a zero velocity? That means it's not moving, right? But a non-zero acceleration? Go ahead.
I don't know. I was thinking, like, do you have to be, like, if you're not the one doing it,
Uh-huh.
like, you can't say that, like, just because you're not walking, if you're in a car, you still have velocity, right? Because
Okay. You do. So that's interesting. You guys are like opening up all kinds of cool physics boxes today. I love this. So it depends on the reference frame that you're talking about in that way. So if you're riding in a car, you're not moving relative to the car.
yeah, like, you're staying in the same position.
Right. But the car, so then I would say that you have a zero velocity and a zero acceleration if you're moving at a constant speed. Because then if you start accelerating, then you would be moving too, right? Yeah, so that's a little bit funny. That's a good idea. I like that. Can I give you an example? So and we haven't really talked about this yet. This is like our next thing. But if I drop the frog, let's look at what happens. If I drop the frog, what happens to him? Tell me about his speed. He accelerates down, right? Yeah. If I throw him up in the air, tell me what happens. As he's going up, what happens to his speed? He slows down. And at the very top, what's his speed? 0. But gravity's still pulling on him. Are you with me there? Yeah. My best example, the one that I can visualize best for this, is when you throw something and it's at the top of its path. It has a 0 velocity just for a moment. Not for a long time, but for a moment. But it's still got a non-zero acceleration. Yeah. How about an object having a 0 acceleration and a non-zero velocity? Is that possible? Yeah.
Yeah, you put cruise control on your car.
Yeah. You're walking down the path, right? Yeah. This one is like the easiest one to imagine. This is like the first 2 weeks of our class. Yeah. Object moving at a constant speed. Absolutely. That's this one. But it's kind of fun to like think about what do those things mean when you put them together, right? What does it mean to have 0 this and non-zero that? It's just, yeah, it's kind of interesting. All right. These kind of making sense? Is that okay? All right. Now we're going to go back to our acceleration equation. So this is that sheet that I told you to make all this space for, and it was going to be great. Here it comes. So the fun thing is that in this equation, if you know initial velocity or final velocity or acceleration or time, if you know 3 of them, you can find the 4th, right? Life is good. This equation says nothing, though, about the object's displacement. Okay? I can't tell you how far it went. And that kind of makes me sad because that's one of the big things that we need to know when we're talking about physics, right? Not only how fast it started and ended and how long it took, but how far did it go? So here's the thing, is that there are 3 other equations that are kind of like pushing this together with our displacement information, and 3 things pop out. Now, I can show you how we get them. I can do the derivation for you. And if you would like me to do that, please let me know and we can hang out during Liberty Time and I can go through it. Because it's really cool and it's not math that's beyond you at all. It just takes an extra 5 minutes that I would rather not spend during class. Does that make sense? So I'm just going to give you the equations and ask you to either trust me or come see me and I can show you how to do them. Because it's really not hard. But again, I just don't have lots of time. So I want to make sure that we have time to use them. So equation number 2 that you're going to write down. Here it comes. Has delta x is equal to 1/2 VF plus VI times T. Equation 3 is delta X, this is my favorite one, equals VI T plus 1/2 AT squared. And equation 4 is VF squared equals VI squared plus 2AT. Go.
So what are those three equations that you just wrote for? Are they all equal to each other?
So they are not, like these two, you could set them equal to each other if you wanted to.
Okay.
So the game is, why do we care, right? Like, why are you telling us all this information? Let me tell you why. I mean, we're going to make ourselves a little chart because I like charts. I feel like they help me kind of organize my understanding of my thoughts. How many different variables do we have in all of these equations? Got acceleration, time, initial velocity, final velocity, and displacement. So we got 5 variables, right? So let's write those down. I'm going to write them down in the order of most exciting or least exciting to most exciting. Delta X, which you would also write as D, right? I've told you that, but I've just, the way that I have it in the book and the way that I have it in the sheet is this way. So that's why I'm going to write it. A and T. So make yourself a little chart. And then along the top, I want you to label them with the numbers of the equations. These are not magic numbers. There's no reason that they're numbered this way, and you do not have to have them memorized in this order. It's just easier to write them as 1, 2, 3, and 4 than to write out the equation in the chart. Are you with me there? Just trying to like make myself a little less stressed. So let's take a look at equation 1. I want you to put check marks in everything that equation 1 has in it. So does equation 1 have delta X?
No, it does not.
It does not. Does it have VI? It does. Does it have VF? Indeed. How about A? And how about T? Okay. I want you to fill in the other 3 columns. Go ahead and do that real quick. Once you've got them, check with your neighbor. I think the easiest way to check with your neighbor is to find out where they have their empty box instead of going through all the check marks. So equation 2 has delta X in it. It has VF, it has VI, and it has T. Equation 3 has delta X, it has VI, it has A, and it has T. And number 4 has VF, VI, A, and T. So if you look at this carefully, each of these equations has something, wait, I messed up somewhere, didn't I? This one, oh my gosh, you know why I did? Because I wrote this down wrong. I am so sorry. Change this right now. Holy cow, totally just made a mistake. I apologize. This should not be a T. That's totally my bad. I apologize. This should be a delta X. I don't know. I was just like AT. That should be a delta X. Good thing we checked. Phew. It's like, that doesn't look right to me. This is better. So fix that. Fix this equation right here. Don't have it written down in your notes that way because that would like lead you so far astray. Or you would check your units when you were doing something like, this doesn't make sense. Carveling totally screwed up. Yeah, that should be a delta x. I apologize. So now if we look at it carefully, do you see that each equation has one thing that we don't know? Or that we, not even that we don't know, that we don't even care about. And this, my friends, is why we write our givens chart. Because now when you read a problem, and we're going to do it in just a minute, when you read a problem, you're going to write down, oh, I've got VF, I've got VI, I've got A, and I've got D. Which equation am I going to use? If I have VF, VI, A, and D, or delta X, which equation? You do not have to have this memorized. I'm giving you this as a tool. Okay? So just take a look. What's the right answer? Which equation am I going to use? Equation 4, right? If you had a problem that had D or delta X, T, A, and VI in it, so I'm missing VF. Which one do I want? I want 3. Is that okay? It's all about looking at this. So Isaac said, do you have to have this memorized? No, of course not. You do not need to memorize things. If that's going to be a distraction, it needs to be put away. Okay? Thank you. I just gave you a fancy orange sheet. It's on cardstock. You need to keep this for the entire year, my friends. This is your key to happiness on homework, on quizzes, on tests. You put your name right here. This one is yours. You can three-hole punch it if you want. Put it where you will not lose it. Put it in the front of your binder if you have one of those fancy binders with the clear front. Okay? Don't get freaked out by the entire thing. I didn't give you this on day 1 because it would have totally freaked you out, right? If you look at the top left-hand corner where it says kinematics and motion, kinematics just means moving objects, and motion. If you look at all of those equations, do you see that you now recognize all of those equations? Okay. You use this on homework. You will use this on tests. It's the same thing, but it's laminated and doesn't have any notes on it that you've written on it. Okay? But they're exactly the same. Like I printed them off and I just laminated 20 of them. Okay? So this is your key. You do not have to have these things memorized. But having this chart as you're getting started will be very helpful. All right? We've got just a couple minutes. I wanted to do some practice, so I'm going to read you a question. But while I'm doing that, I want to make sure that you have written down your homework for today. I want you tonight, I should say, before I see you again, to work on, let's say, don't do 22 and 23 yet. We'll go back to those later. So on page 57, I want you to work on number 2, 3, B, and C, 14, 18, and 20. So the game is in all of these problems to figure out which equation to use. So we've got 2 minutes. I'm going to read you question 20. Okay? I want you to, oh no, I don't want to read you 20. Sorry, I lied. I want to read you, I'm going to change my mind. Haha, this is what I do. I apologize. Lies, we're not going to do 20. I want you to do 22 instead. Question 22 says, a car starts from rest and travels for 5 seconds with an acceleration of 1.5 meters per second squared. Oh, that one's never, it's too hard. I wanted to read one that you could just look at, and this is not working very well. Let's look at 14. Is that one better? No. I'm a failure. Hold on. I wanted to have like 2 more minutes. That's my problem. Hold on. Wait for it. Here it comes. Don't leave me. Stay with me here. All right, here you go. Ready? A car accelerates uniformly from rest. No! To a speed of 6 meters per second in 5 seconds. How do you find the distance? Can you do that? You think?
Yeah, anything's possible.
I love your optimism. Do it for tonight.